again, this is just a different curve, but it's a very similar curve. It's, this curve, the curve that's on here, and I can run this paper off for you. I posted it already on your Blackboard site. So on Blackboard, you can see it in color. If I run it off for you, it'll be in black and white. But X and Z are creating a circle. Y is just linear. So, you know, picture a slinky just being stretched out in the Y direction. That's what this curve is. And so I calculated T, N, and B for certain points. So here's 1.0 pi, -2 is a point on the curve, and I used some other software that drew a bunch of little T and B frames. This was the one particular I decided to focus on. The N is pointing into the curve, so it's the y-axis is this one here, because the slinky's being stretched out in the y direction. So from this point, the N is pointing kind of more straight up in the z direction, and the binormal is kind of pointing out in the y direction. But I don't know if these are perfectly perpendicular. I mean, the three vectors are perpendicular, but I don't know if this is exactly in the z direction. It might just be close enough that it looks like it.
Based on your calculations you have out to the side there, I think that one actually is.
Yes, yeah, you're right. Yeah, 0, 0, 1, yes, it is. Yeah, it's pointing straight up in the z direction. Okay, so there's a name of a plane, we call it the normal plane, and it contains the vectors n and b. T is its normal vector. Remember, those three are perpendicular to each other. So the normal plane contains n and b, which, okay, that makes it, we're calling it the normal plane, so it makes sense that it contains the normal and the binormal. Those are the vectors that lie in the plane. This vector is supposed to be perpendicular to the plane. It's just, on a 2D picture, it's a little hard to show all that. But T, which is perpendicular to both of them, is that plane's normal vector. Okay, so again, in terms of physics and designing roller coasters and roads and stuff like that, you know, often people are interested in, you know, what points in space are lying in these certain planes. So that's why we kind of give them names.
So the pink is the acceleration?
The pink is the binormal vector, which is the cross between the tangent vector and the normal vector. There's another plane called the osculating plane. And the osculating plane contains the tangent vector and it contains the normal vector. So remember how you calculated V? You calculated V by taking T cross N. So the osculating plane contains T and N, thus it has B as its normal vector. It is the plane in which you can see the curvature the best. Okay, because in that plane, you can draw a circle that's tangent to the curve. And so at this point, I mean, again, at every point on any particular curve, the curvature might change. This is a pretty good example where, you know, you could see the circle pretty tangent and following the curve. So in that plane, there's a circle that we call the osculating circle. And the osculating circle does a good job of sort of showing you the curvature. So if you continued on the particular curvature, so remember kind of like you're traveling along the curve, and what if you kind of continued on the tangent and kept going at that same curvature, the circle sort of showing you what the consistent curvature would be at that point. And the radius of the osculating circle, again, remember, this was a different example than the one that we just did. The radius of this circle is the reciprocal of the curvature. So, for our example here, the radius, the one that we've been working on, the radius of the osculating circle is 36 fifths. So again, think about it, the bigger K is, the more curvy, the smaller this circle's going to be. You know, picture something really curvy, a really little circle would have to fit inside that curve. The more smooth it is, the bigger that circle's going to be. The more flat it is, the bigger the circle's going to be. So in this case, our radius is, you know, relatively big for the example that we were just doing. I would draw that circle. I'd have to think through how to find the equation of the circle, because we have the radius of it. The center should be on a perpendicular line from our point. It could be worked out. I think at the moment I'm not going to try to spend time doing it in class right now, but I could probably make a second handout and post on Blackboard that kind of has all these same things for the curve that we've been working on.
Our point is